So here's a question, and this is a question that manufacturers of soda drinks definitely deal with, and they have people, mathematicians, probably working on kind of answering this question for their specific cases. But say that you work for Coca-Cola, maybe you're a mathematician there, and you need to determine the dimensions in centimeters of a Coke can, which minimizes the amount of materials used given the volume must be 350 milliliters. Okay, so that's the question, and optimization questions will be like this. They'll be extremely long, there'll be word problems, and you kind of have to interpret the word problem and arrive at a conclusion. I've already done the first step, which is to draw a diagram, so here it is on the left here. And the next thing that you want to do, as soon as you draw a diagram, the next thing that you want to do is, if we go back to our steps, you probably want to choose a variable to optimize. So for us, you kind of have to read the problem and look at what they're asking you to do. So you're working for Coca-Cola. You want to determine the dimensions. So here are the dimensions of a Coke can. And I should say that this Coke can is cylindrical. I forgot to write that in. I'll just add that in now. Cylindrical. Okay, so cylindrical meaning that the Coke can resembles a perfect cylinder. Now, of course, Coke cans are not going to do this, but this is a simplification to the problem so that it's easier to solve. So you want to determine the dimensions. In this case, a cylinder's dimensions is made up of the radius and then also the height. Okay, so we want to determine those two things, and we want to do it in centimeters. And what we want to do is we want to find an R value, a radius, and a height such that the amount of materials that we use is minimized. Okay, so as soon as you see the word minimize or maximize, that gives you a hint, like, those are the quantities that you're optimizing. For us, we're interested in minimizing the amount of materials. And if you think about it, the amount of materials that are used to make a Coke can is, uses some tin, maybe some aluminum, and the amount of tin and aluminum that you use is proportional to the surface area of the cylinder, right? Because only the outside of the Coke can is going to be made up of that metal material. The inside is going to be filled with Coca-Cola or whatever drink you want of your choosing. So here, the question doesn't even tell you which variable to optimize, right? It just says, minimize the amount of materials used. But here, what they're really saying is minimize the surface area of this Coke can. And so already you can see that it's challenging because you have to interpret the word problem and clearly identify what the variable you're going to be optimizing is. Okay, so I'm going to write this down. What we're going to do is, maybe I'll say want. Okay, so we want minimum, or maybe I'll say want to minimize surface area. Okay, and that's very important to recognize. You might even want to write it down. You have to identify what variable you want to optimize for. Now, the other thing that's important to do is give letters to things. I've already done this, but here I'm saying the radius is the radius of the cylindrical can. The height is the height of the cylindrical Coke can. And now I've introduced a third variable, which is the surface area of the can. So it's a good idea to write down what variable you're going to be using what variable you're going to be using to represent surface area. I'm just going to use the letter A, but you can use whatever you want. Okay, now the other thing that they give you is they say that, the volume must be 350 milliliters. I had to look this up earlier on the internet, but the volume of a Coke can is roughly 355 milliliters. I've simplified it to 350, which is close enough, but a little bit nicer number. But you need this piece of information that the volume is constant. It's always 350 milliliters seems to be important. And this is what's called the constraint. I'm gonna underline this. So the volume must be 350 milliliters is the constraint. The constraint is just a set of conditions that the optimization problem comes with. And here the condition is that the volume is constant. The volume is always 350 milliliters. Now, if we take a look at our cylinder over here, you might remember that the volume of a cylinder you can find by taking or finding the area of the base here. The area of the base is just the area of a circle, and then multiplying the area of the base by the height of the cylinder. So pi r squared times h. Now, what they're saying is this volume is actually a constant. It's not a variable. This is another important idea. You have to separate in your mind. You have to separate constants from variables. So the volume here is just a constant. It's fixed. It's 350 milliliters. Okay. And now you can see that as soon as you fix the volume, you can see that there's an implicit relationship between radius and height, and that's going to become important later. So here you can think of radius being a function of height and height being a function of radius implicitly. These two variables are interdependent because the volume is fixed. Okay, so going back to the original problem, we want to minimize surface area. Okay, that's what we want to do. Let's first write down the equation of a surface area. So the surface area of a cylinder, it has two circular bases, one on the top, one on the bottom. So we're going to need 2 pi r squared. And then the cylinder also has this area here. The area that kind of wraps around, and you can find that area that wraps around by taking the circumference of a circle and multiplying by the height. So that's going to be 2 pi r, which is the circumference, times the height. Okay, and so that's the surface area of a cylinder, and that's what we want to minimize. Okay, that's the variable. So here a is the variable that we want to minimize, or you can think of a as the dependent variable. You can see that area here is dependent on two variables, radius and height. Okay, so we have radius and height. And so actually right now, I'm going to erase a for just a second. I'm going to replace a with a r comma h in function notation. So what I'm saying here is that the area here is a function of two variables. So the area here is a function of two variables. It depends on the radius and it also depends on the height. Calculus 1, and that's kind of the calculus you guys are doing. In DP1 and DP2, you guys do calculus 1. Calculus 1 revolves around single variable calculus. And so our goal is like, sure, we can optimize for the area, but before we do that, we need to express the area function in terms of one variable. It can't be in terms of two variables. So what we need to do is somehow find a relationship between r and h in such a way that we eliminate one of the variables. And we have that relationship right here. That relationship is just the constraints, okay? So what we're going to do is we're going to try and turn this from a two variable function to a one variable function. Remember what the goal is. The goal is to minimize surface area, okay? So like I'm going to do a really bad sketch here, but say that this is the area and this is the radius. You want to minimize the surface area, and to minimize the surface area, you're going to have to find the stationary points and then also consider the endpoints. But to find the stationary points, you're going to first have to find the derivative and set it equal to 0. Well, to find a derivative, you first need a function in terms of one variable. It can't be in terms of two variables. We don't know how to differentiate two variable functions, okay? So the first step is to reduce the optimization variable and express it in terms of from a two variable function to a one variable function. Okay, so how are we going to do that? Well, we're going to use this piece of information right here. So if I isolate for h, we get 350 divided by pi r squared. I'm gonna take this. Okay, so we have height. Height is 350 divided by pi r squared. I'm gonna take this. Maybe I'll circle it, and I'm gonna substitute it in for h. Now, as soon as I make that substitution, notice that the function goes from a two variable function to a one variable function, and that function is now the surface area is now a function of radius only. So if we replace the h with its equivalent counterpart, 350 divided by pi r squared, now we have the surface area expressed only in terms of the radius. Okay, now we're going to do some simplifications. So here the pi's cancel, and then also 1 factor of the radius cancels. So what we're left with, after we simplify, we get 2 pi r squared plus 2 times 350 is going to be 700. And then we also have 1 factor of r in the denominator. I'm going to move that up and write it like this. The reason I'm writing it like this is because the next step is to find the derivative of the area function. Okay,